homework 3 is due, I guess, tomorrow night. So make sure you get that in by the end of the day on Thursday. And quiz 3 is on Friday. So I guess the topics aren't TBA. I actually have a review for you in class. But let me just write down what this quiz is going to be on. It's going to be on standard deviation and normal distributions. Topics, standard deviation. Oh, yeah.
I just had a question. I kind of struggled with the number 4 on the homework. Can you like go over a copy
Yeah. Why don't we go here to assignments? Homework. Is it homework 3?
Yeah.
Let me just take a look at this one. So let's see. Oh, okay. So number 4, we're actually going to go over an example today. So yeah, we haven't really covered that yet. So that's probably why you're struggling a little bit with that one. All right. Any other questions on the announcements? All right. So what I'm going to do, let me just try something here. I'm going to mute myself here. And I have a new set of guided notes. Oh, yeah. Yes, I do. Yes. Sorry, I'm a little bit flustered. I went to Chick-fil-A and now I'm like kind of going a little crazy. I actually decided to try this out since it's kind of hard to like read the board over here. And since I have a nice iPad, I can kind of just write on the notes. So we're going to see how this works today. If it doesn't work, then we'll see. So 30.6, we're going to start talking about distributions, okay? So I guess first we have to talk about what a distribution is. Pretty simple to kind of go through the like what it is, okay? So before we even define what a distribution is, let's look at this histogram. So this histogram represents the lengths of words in the Snapcases book, okay? We can see that, let's see, there's a lot of words of length 4, and then a little bit length 7. If you go out this way, there's 3 and 2 and 1. So if you were to describe this histogram to someone who couldn't see it, what would you say? What would you tell someone? What are some of like the biggest trends going on here? Oh, TJ? Mm-hmm. Mm-hmm. Yeah. So at first it increases up to 4 and it like hits a peak and then it decreases after, right? Any other ways we describe the system? Is there like more information on the left-hand side or more information on the right-hand side? On the left, right? So let me just write that down, okay? So maybe there's more info on the left, okay? And anyone else want to kind of describe it? Yeah, I don't really know if there's anything else. There's a peak at 4, increases up to 4, then decreases after. More information on the left-hand side than on the right-hand side. And that's about it, okay? So what I want you to do now is we're going to try to draw a picture of this graph by sketching like a smooth curve that approximates like the heights of the histogram, but not actually drawing the bars, okay? So how about this? I'm going to draw a little line here. I'll still keep 4 in the middle since 4 seems to be the middle value here. And imagine like kind of drawing a line on top of the histogram, okay, kind of like that, okay? So if I were to draw this, I would try to make it seem like there's more information to the left, and then it drops off a little bit more quickly once I hit 4. Okay, that's, I didn't draw it very smoothly, okay? Should be a little bit more smooth here. Like that. Okay. So sometimes when we want to describe a distribution, but we don't actually want to create the histogram, we like to draw something called a distribution. Okay, so this is called a distribution. And it's a way to approximate a histogram without actually drawing it. So there's less detail, but you can still describe the graph to someone if they're wondering. Is that a fan? I was wondering what that sound was. I was like, well, what is this? Okay, so are we good with what a distribution was? It's kind of just like a picture of the graph without a lot of detail. Okay, so histograms usually describe a sample since we have a few things to graph. Usually our sample size is pretty small. Distributions pretty much are used to show trends that we either know or predict the population is going to have. So over here, we have a distribution, and we can kind of predict, even though the histogram kind of describes a small sample of things, the distribution generalizes everything to the population. So we can kind of predict that the population kind of looks like this. One other thing about distributions is the vertical scale. I didn't draw a vertical scale, but let's just pretend I did. We usually make these drawings represent like the entire population or the number of things that we're interested in. So if we were to take this graph and like shade in everything below it, okay, everything underneath this graph would describe every single thing that can happen in our population. So 100% of the cases are underneath the curve. There's no other like weird bars that come out on the right. Okay, so 100% of the information is below this curve. Okay, and this curve kind of just shows general trends in the graph, makes it really easy to understand what's going on in a really simple way. Okay. Any questions on what a distribution is or how we kind of estimate a graph if we were given a histogram? All right. Let's flip to the next page. Okay. Now distributions can have different shapes. Okay. So our distribution, the last one, kind of look like, you might say it looks like this one, might look like this one. But usually it's a little bit more obvious what shape things have. Okay. So let's take a look at this one right here. Okay. This distribution up here has a lot of information to the left-hand side. Okay. And then a little bit less to the right. There's more extreme values to the right. Does everyone kind of see that? Okay. So there's actually a name for the shape. It's called right skewed or skewed to the right. Okay. So whenever we see a distribution, okay, looks kind of symmetrical, but there's a little tail to the right where there's extreme values. More of the information is pushed towards the left. We call that skewed to the right. Okay. On the other hand, this graph has a tail to the left, right? Most of the information is towards the right-hand side of the graph. And then we have some weird extreme values towards the left-hand side, okay? We call this graph skewed to the left or left skewed, okay? And finally, if our graph looks perfectly symmetrical, nothing to the right and nothing to the left, we call that symmetric, okay? The reason we call that is if we draw a vertical line right through the center, well, the left-hand side is pretty much the same as the right side. So symmetric, left skewed, and right skewed. Any questions on like the different types of shapes things can have? I think it gets a little confusing because I feel like when I ask students, okay, is this skewed to the left or skewed to the right? They see like most of the information on the right and they're like, oh, that's skewed to the right, because most of the information is here, right? The skewness actually describes where the tail is, right? So if the tail is on the left, it's the left skew. Okay. Now let's take a look at these, not 3, but 2 histograms, okay? Now, let's take a look at how these are kind of similar. Well, both of them look symmetric-ish. This one might be skewed to the right, but still kind of symmetrical, right? So most of the data points are at the center of the data of the distribution, right? If we were to draw a distribution, let me choose a different color here. Well, it looked like this and something like this, right? So most of the data points are at the center. They seem to be a little symmetrical, which means like on the left side would pretty much be the right side, right? Okay. There's actually a special name for this distribution. Okay. If I were to kind of draw the distribution, it would look like this. Does anyone know what this is called? The normal distribution. Good. Let me write that down. It actually has another name. Does anyone else? Yeah, the bell curve, right? Okay, so of course, bell curve because it looks like a bell, right? It's actually called a normal distribution because it happens a lot, okay? So, for example, heights of people, normally distributed. The weather outside, normally distributed. I don't even know. I'm trying to think of different examples. The length of your hair, normally distributed, okay? Whenever we have a lot of factors going into something like the temperature or the weather or your height, a lot of different factors going into one number, it's probably going to have a normal distribution. Okay? So this happens so much that statisticians have called it the normal distribution. And they've actually done a lot of work into figuring out what percent of the population fits in between different sections of the normal curve, okay? So let's turn our page again, okay? So some things about the bell curve or the normal curve. I just went over this part. One special thing about this curve, let me just draw it again so you can kind of see it, okay? The mean, median, and mode of a normally distributed data set have the same value. Right in the middle, right? So, for example, the mean has to be in the center, right? The median is the middle, and the mode, well, that's where the highest point is, which is also the center, right? So the mean, median, and mode are right in the middle. And I just cut off what I was about to say next. Okay. So now we're going to talk about some symbols, okay? And this just makes it easier for me to write when I'm about to write next, okay? Let me show you some symbols that I'm going to be using. Whenever I want to talk about the mean, I'm going to use this symbol right here. Okay, it looks like a U with a little line on the left. Okay, it's actually the Greek letter U. Okay, but that's what we're going to use. You might want to practice drawing some of these kind of weird. Okay. And we learned about standard deviation on Monday, right? Okay, we have a special symbol for that too. It's a circle with a line on it. We call that the Greek letter sigma, lowercase sigma. So, yeah, it looks like a cherry, doesn't it? Wait. I'll make it red. Okay, so I'll just write the Greek letter if you want to know, mu and sigma. All right, so if you see me use these symbols in the next page, that's what I'm talking about. Mu for mean, sigma for standard deviation. Okay, so I have 3 graphs here, okay? these graphs are going to become very important in the next set of questions that we're going to talk about, okay? So what I have here is I have our bell curve, okay? So this sort of, this topic that I'm going to talk about only works for normal distributions, okay? And I have like little tick marks on the bottom, right? Okay. Now, what these tick marks represent, like for example, we could put like 0, 5, 10, 15 on the bottom, just like a regular x-axis. I'm going to make each of these tick marks represent one standard deviation, okay? So like from here to here is one standard deviation, and from here to here is another standard deviation, okay? So one tick mark, I don't want to write it there. I'll write it here. One tick mark equals one standard deviation. And remember that the symbol for standard deviation is the cherry, right? Okay. So let's kind of label this graph. Okay. Right in the middle, we know that the mean, median, and mode is right smack in the middle. Okay. I'm just going to focus on the mean for now. So I'm going to label this with my mean symbol, the mu. Okay. So just labeling it mu. So if the tick marks represent one standard deviation, what's the label for this tick mark? The cherry symbol goes there, yep. But it's not like that is the standard deviation. Like on the x-axis, this really is the standard deviation, but it's the mean added to the standard deviation, right? So technically, our label here is the mean plus the standard deviation, right? So I just took that mean, I added on one standard deviation. Okay, what do you think this tick mark symbol should be? Yes, it's the mean plus sigma plus another sigma. So the mean plus 2 sigmas, right? So this is the mean plus 2 sigma. And then I guess if we go on, this is the mean plus 3 sigma, right? Okay. Oh, we can also subtract off the standard deviation, right? So over here, this would be the mean sigma, right? So mean mu minus sigma. And just working backwards, we have the mean minus 2 sigma and the mean minus 3 sigma. Okay, so all we're doing is putting the mean in the middle, adding and subtracting off standard deviations. Okay, now I'm gonna just kind of fill in the other one so I don't have to keep doing it. Okay. This might take a little while, I'm sorry. I'm actually gonna kind of cheat here. I'm gonna take this. Oh, no, that's not what I wanted. Nope. Copy it. Paste it. There we go. No, that's not what I want. There we go. Okay. So let's do this. We're going to focus on the first graph. And what I want you to do is I want you to section off the first tick mark below the mean all the way to the first tick mark above the mean. So from the mean minus sigma to the mean plus sigma. Okay. And what I'm going to do is I'm going to shade in everything below the graph. So everything between negative sigma and positive sigma. Okay. And let's kind of like describe what part of the population this is. So how would I describe everything with the mean minus sigma and the mean plus sigma? I've even got a kind of simple,
Is it 68, 97?
yes, we're getting there. We're getting there. We're getting there. Good. It's a good observation. I'm actually going to just call this within one standard deviation of the mean. Okay, so that makes sense, right? Everything in this little shaded area is definitely within one standard deviation. Like if I'm here, well, I'm still one standard deviation away from the mean. Right? Over here, I'm still within one standard deviation. Okay, so when I talk about things being within something away from the mean, this is kind of what I'm talking about. Either add or subtract, okay? Now, I'm gonna make Alicia happy here. I'm gonna label this, and statisticians have done a lot of work with one standard deviations, two standard deviations away from the mean. And they've discovered no matter what normal distribution you're working with, 68% of the population is within one standard deviation from the mean. Okay? So 68% of the population are between this value here and this value. Any questions on this graph here? Okay. Let's go to the next graph. Well, I guess you can guess where I'm going here. I'm going to section off the two standard deviations. Describe this shaded area within two standard deviations of the mean, right? So this is within two standard deviation of the mean. Okay. Statisticians do a lot of work with this too, and they've actually figured out that, they figured out that 95% of the information are between -2 standard deviations of the mean and +2 standard deviations of the mean. Okay. So we got 68, 98, 95, sorry. And I guess you can guess what I'm shading in over here. I'm shading in 3 standard deviations away from the mean. Okay, so I guess I'll draw it. This is within 3 standard deviations of the mean. My handwriting is getting kind of bad here. Does anyone know the last percentage? Very, very close, very close. You have the right idea. It's 99.7%. Okay. So pretty much all the information is within 3 standard deviations of the mean, maybe a little bit on the other corners, right? But we definitely know that 99.7%, pretty much all the information is within 3 standard deviations of the mean. Okay. Any questions on these 3 percentages here? Okay. We actually have a name for this. It's called the 68, 95, 99.7 rule. Pretty creative name there. For a normal distribution. This is also called the empirical. And what this states is as long as we know that the distribution is normal, 68 will fall within 1 standard deviation, 95 between 2, 99.7% between 3 standard deviations. Okay, let's see how we can ask questions about this sort of topic here. Okay, so we have the scores on a test are normally distributed with a mean of 65 and a standard deviation of 8. Okay, what score, or how would I find what score is 1 standard deviation above them? What would I do here? Alyssa? Yeah, right? we would do 65, which is our mean, plus 8, right? We're just adding a standard deviation to our mean. Okay, I'm really bad at mental math, so I actually did this in my office. I got 73. Okay, so using our symbols, we could even label this, right? 65 is our mean, 8 is the standard deviation. Okay, below the mean, I guess I would subtract, right? So 65, 65 minus 8, and that is 57. Okay, so what percent of students scored between a 57 and 73? 68. Yes, sorry, I checked my notes there because I forgot. Yes, 68% of the data scored between 57 and 73, right? If we drew our graph, oh no. If we drew a graph, 57 and 73 would be within 1 standard deviation of the mean. So that's why it's 60, right? Okay. One thing about these types of functions, I do require you to memorize the 3 numbers, 68, 95, 99.7. Make sure you memorize them and make sure you know which number they correspond to. 1 standard deviation away, 2 standard deviation away, 3 standard deviation away from the mean. Okay, let's do one more and then I'll have you try one on your own. What score is 2 standard deviations away from the mean? How would I find that? Yeah, so you took the last score 73 and added 8. Is that what we did? That's a good option. I'm just going to make it a little bit easier to think about in my head. I'm going to take our mean and add the standard deviation twice, right? Okay, you could just add 8 to 73. Okay, and I got 81. Okay. Below the mean, I guess we have 65 minus 8, right? And that gives me 49. But now we're within 2 standard deviations of the mean, which means what percent scored between a 49 and 81? 95, good. So 95%. Okay, those are one of the numbers we have to memorize. Okay, how about this? I'm gonna give you 3 minutes. Try the last 2, E and F. See what you can come up with, and we'll come back together really soon.
We don't talk about Bruno, no, no, no. We don't talk about Bruno. But it was my wedding day. It was our wedding day. We were getting ready and there wasn't a cloud in the sky. No clouds allowed in the sky. Bruno walks in with a mischievous grin. Thunder. You telling the story or am I? I'm sorry, Vivi, to go on.
Okay, so I got Alyssa to write up her answers here. I like how you did 3 times 8, right? So I think Alyssa realized that instead of writing minus 8 or plus 8 plus 8 plus 8, you can kind of just combine that into 3 times 8, which is really good. Okay. If that doesn't make sense to you, well, we can always write this 65 plus 8 plus 8 plus 8 and get 89, right? So either way of writing it's totally fine. Okay. So what percent of students scored between a 41 and an 89? 99.7, awesome. Okay, so that's all we need to know for the empirical rule. All right, any questions on the empirical rule? All right, let's flip our page again. Okay, so I guess we kind of talked about how the standard deviation actually helps us understand things. And we talked about how we can know, like, we talked about if we're given a distribution, well, we have our mean in the center and we have our tick marks for standard deviations, right? But what if I don't want to go within 1 standard deviation? What if I want to go like 1.2 standard deviations or 5.8 standard deviations away from the mean, right? There's actually a way to do that. And we use things called z-scores, okay? So z-score, I'm trying to figure out where to put it. Okay, there we go. A z-score. A z-score is literally a fancy name for the number of standard deviations away from the mean that a data value is, okay? So, for example, let me give you a few examples here. Okay, let's say we had a normal distribution and in the center we have the mean, right? And let's say these tick marks are still one standard deviation, okay? Okay, so the mean plus sigma, the mean plus 2 sigma, the mean plus 3 sigma, and so on, right? Let's say I wanted to figure out what data value represents right here. The mean plus sigma and then a half, okay? Well, this point here is 1.5 standard deviation above the mean, right? Right? So basically another way of saying that, instead of writing that huge thing out, we can literally write z equals 1.5. Okay, so just another way of saying that something is 1.5 standard deviations above the mean. Okay, let me give you another example here. Okay, let's say I had let's say I had mean minus sigma, mean minus 2 sigma, mean minus 3 sigma. Okay, what if I wanted to do, I don't know, this point, which is 2.8 standard deviations below the mean. Okay, so let me just write that. 2.8 standard deviations below. Anyone want to guess what z-score that would be? 2.8, but how can we show that it's below? Negative, right? So we're going to make the z-score negative to show that the x value is below the mean and not above the mean. Okay. So z-scores can be any, so, oh yeah.
Sorry, can you have a z-score that's like more
Yeah, how about this? So for example, we could go all the way out here. Okay. What if we were like, let me just make it green here. What if we have this value here and it's 6 standard deviations above the mean? Well, z could be 6, right? So z could be literally any number. We could have a z of 1,000, even though that would be kind of crazy, right? Yeah, so our z-score can be any number, negative or positive. That's a good question. All right. Now, so let's see. So we know that the z-score is the number of standard deviations above or below the mean. Let's talk about how we actually calculate it. Okay? So let's pretend we're given a data value x. So for example, a student's score on the exam might be x, okay, from a normal distribution, and we know what the mean is, and we know what the standard deviation is. Okay? To get the z-score, we would plug it in this formula. Z equals our data value minus the mean all over the standard deviation. Okay? If that's not making sense, I think an example is going to help us out here. Okay, so let's take a look at this example. We have a teacher. They gave 3 different versions of the test to her students. All of the versions were normally distributed. So version 1, version 2, version 3, all look like that bell curve. Test version 1 has a mean of this, standard deviation. Oh my gosh, there's so many numbers flying around. How about this? Let's organize our information first, and then we can solve the problem. Okay. So it says that test version 1 had a mean score of 66. So under version 1, I'm just going to write 66. Okay. And a standard deviation of 4. Okay. Test version 2 has a mean of 66 and a standard deviation of 2. And test version 3 had a mean of 72 and a standard deviation of 6. Gosh, these tests don't look so good. That's okay. All right, so what I did here is I just kind of organized my information so I don't make mistakes when I try to put things in. This is always a good practice when you're given a word problem with a lot of information. Okay, let's take a look at number 1. Lewis, he received a 76 on test version 3. We're asking to find his z-score and what it means in terms of standard deviation and the mean. Okay, so we have 76 here. What value is that in our equation? X, right? This is the data value that we're interested in finding the z-score, okay? So before I even go on, I know this sounds kind of stupid, but I always make mistakes. What I'm gonna do is I'm gonna write in all of the different values in our equation. So I'm gonna write z, x, mean, standard deviation. I know it might be overkill, but I think it's helpful, okay? And let's see, we have the mean of, this is version 3, right? So our mean is 72, right? Standard deviation is 6, x is 76, and we don't know z, right? That's what it's asking us to find. Okay, well, I guess we can plug it in, right? We have z equals x minus mean over standard deviation. Okay, well, I guess all I have to do is plug in everything in the right? So x is 76, the mean is 72, and the standard deviation is 6, right? Okay. 76 minus 72 is 4, 6 stays on the bottom. And when I divided this out, I get 0.667. Okay. So my z-score is 0.667. What does this number mean in terms of the standard deviation? TJ?
It's 0.667 above the mean.
Yes, right? It's positive, so that means Lewis did better than the mean, right? So he scored above the mean, and he scored 0.667 standard deviations above it. So I'm going to write this. Lewis scored 0.667 standard deviations above the mean. Okay. So not too bad, right? We're kind of conglomerating our information into like one big pile. We plug it into the equation and we solve for z. If z is positive, you score above the mean. If z is negative, it's below, right? Okay. Try number 2 together or on your own, and we'll come back in a little bit. So I got Bailey to write up on number 2. Do you kind of want to take us through your steps here? Mm-hmm. Oh, it was 70. Oop. Mm-hmm. Mm-hmm. Awesome. Okay. Let's just talk about what this means. Z is negative, right? So that means we're below the mean. So Jamie scored, okay, I'm gonna write 0.333. Oh, standard deviations, right? Below the mean. I'm gonna be a little nitpicky here. Probably won't take off points for it, but we didn't score negative something below, right? So if we're trying to conceptualize this answer as to like what it actually means, we can't score like something negative below something, right? So technically we scored plus 0.33 as long as we write that it was below the mean. Does that make sense? Okay. Yeah.
We need that plus sign.
Oh, no, you don't really need the plus sign. Any questions on number 2?
You have to write just like SD when you write out like statement.
You can abbreviate, that's fine. All right, any other questions on number 2? Okay, next class, what we're gonna do, we're gonna talk about what happens when we're going the other way. So when we're given an X value and we're trying to find, or we're given a Z score and we're trying to find the X value, things get a little bit different, okay? We'll talk about that on Friday. But for now, we have a quiz on Friday, so we should probably prepare for that. Okay. So I printed out a quiz review. There's a front and a back.